This video is going to introduce bootstrapped confidence intervals. That is, confidence intervals calculated from the bootstrap method. Specifically, this is going to be percentile-based confidence intervals from the bootstrap method. This is not the standard version of confidence intervals you might find in a textbook, but I particularly like this version of confidence intervals, not because of any particular theoretical advantage, but rather because of the general approachability from this method. Now, it may not be the easiest, in your opinion, the first time you see this method, but I think overall that this is a really easy way to understand confidence intervals following the bootstrap video we just looked at. So we are going to continue on with that bootstrapping idea that we had previously, and we're going to use a smart use of percentiles to help us quantify our uncertainty in estimates of population parameters. That is, we're going to use the bootstrapped sampling distribution to provide for us a range of values with which we are somewhat confident that the true population parameter lives in. Okay, it comes along with a rather simple interpretation, and in fact that's what I'll do first in this video, is just two quick examples in R. And from there we will come back to this application where I can draw pretty hand-drawn pictures for you to discuss the rather theoretical meaning of confidence intervals. So let's just jump into R and get started. So what I've gone ahead and done, but saved for the bootstrap video, is come up with two vectors of capital R bootstrap resampled means. So here are the first 6 observation of bootstrapped resampled means, where the original n observations came from a gamma 2, 3 vector of random variables. Okay, so we have theoretically then these bootstrapped resampled means from which we could make a density plot. We'll first stick the data into a data frame and then go ahead and use ggplot to make a density plot. So here is the sampling distribution of the sample mean for data that originally came from a gamma 2, 3 population. What we're seeing from the sampling distribution is that the most likely values for the sample mean are centered around 0.67. Now I know that's actually a reasonable guess because for the 2 parameters for a gamma distribution, the expected value is 2/3. And indeed, our sampling distribution is centered around a really good guess for the population mean. But what's more, from this sampling distribution is that we can actually provide a range along this x-axis here, I'm trying to highlight with the mouse. We can provide a range based on percentiles that'll allow us to say with some confidence an interval with which we are somewhat confident that the true population mean lives. And in fact, we can use percentiles, called quantiles in R, to calculate. Let's start with 0.1 and 0.9. So if we calculate the 10th and 90th percentiles from our vector of sample means, what we're actually doing is putting 80% of the observations in between the 10th and 90th quantiles or percentiles. So here, 0.66, that's like this value here, and 0.68, that's like this value here. So in between here, the 10th percentile, and here, the 90th percentile, is 80% of the sample means. We would say, from this confidence interval, we are 80% confident that the true population mean, because we calculated sample means in this bootstrap resampling, that the true population mean is between 0.65 and 0.68. Now, let's add this as a comment, so it's because we're recognizing it's not actual code here. Now, if we were interpreting this in context of data, we'd want to say what that population mean represents and specify the units of the population mean. We don't have that in this example, so we'll just continue with this general discussion. Okay, let's just do one more example so you can start seeing the pattern of these sentences that follow from these interpretations. So here is a vector of R bootstrap resampled standard deviations from the same original population. And let's just kind of repeat the same process we looked at before, where we can first make a plot of the estimated sampling distribution for the sample standard deviation. And we're going to make a similar sort of interpretation of some confidence interval estimated from the bootstrap resampled standard deviations. I'm picking some different percentiles this time so that we can see a variation on the interpretation. So now we picked out the 2.5th and 97.5th, I don't really know how to say that, percentiles. Well, if you look at these numbers long enough, what you're realizing is that in between, let's see, 0.45, something about here, and 0.49, let's say something about here. So it's actually from here to here, now that I look at the scale better. We would say in between this 2.5 and 97.5 percentile, there is 95% of the sample standard deviations. So we would interpret we are 95% confident that the true population standard deviation is between 0.45 and 0.49. And again, let's just make this all one sentence here. Now the things you got to pick out that separate this second example from the first is here we have bootstrap resampled standard deviations. So we reference the true population standard deviation in this sentence. Second, we chose percentiles that put 95% of the resample standard deviations in between these two percentiles. So that makes for us a 95% confidence interval. These are the general interpretations that I want you to practice and rehearse. I would like them to look exactly like this, albeit in context of the data, where you remember units on the end. Back here where I can draw some pictures for you, we are going to discuss the theoretical meaning of P% confident. This is where a weird interpretation shows up. If you think back to the bootstrap procedure, which is inherently random because we are randomly selecting or randomly resampling observations from our original vector of data, if you went out and resampled that same vector of data and I went out and I resampled that same vector of data, we'd probably get different indices. That's what we mean when we say resample this thing. So not only is the bootstrap procedure itself inherently random, but we're also imagining that we have randomly sampled data from some population of interest. So there's actually like 2 layers of randomness going on here when we try to create confidence intervals to estimate a population parameter. So I'd like you to imagine it like this. I'm going to draw a vertical line that represents the, let's say, population mean, mu. And when you resample these confidence intervals, what I'm imagining is that if I went out and got a confidence interval, it might contain the true population parameter. That is to say, the lower bound of my confidence interval starts there, and the upper bound of my confidence interval ends there. But if you went out and took your own sample from the population and Bootstrap resampled it and estimated a confidence interval, maybe you'd get something like that, slightly shifted. And if your friend went out and took their own random sample from the population, maybe they'd get something like that. Because we are each taking, this is me, you, and your friend, because we're each taking our own sample from the population, we are going to get layers of randomness showing up that are going to shift our confidence intervals ever so slightly about the true population parameter we're estimating. And the idea is to continue to imagine that you went out there and you and your friend and your friend's friend's friend and your friend's 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 friend each calculated their own bootstrap confidence interval. Some of those confidence intervals would include the true population parameter. Some of them, I will highlight now, some of the confidence intervals which might not capture the true population parameter just by chance. When we say we are p% confident, what we're actually saying is if you and a theoretical infinite collection of your friends each took a new sample from the population, and each of you calculated your own confidence interval, p% of those theoretical confidence intervals would include the true population parameter of interest. And 1 minus p% of those would not. The weird thing about confidence intervals is they are actually statements about theoretical resamplings from the original population. And under each theoretical resampling from the original population, that p%, whether it be 95% or 80%, that p% of those theoretically resampled and calculated confidence intervals would capture the true population parameter, whatever number it might be. The thing you got to remember, though, is even if you are 80% confident, 20% of those confidence intervals won't capture the true mean. And even if you create 95% confidence intervals, 5% of those confidence intervals won't capture the true mean. Now, the real trick is we all want to be 100% confident, but the only way we can absolutely be 100% confident is the following interval, which I guarantee will capture any parameter you're interested in. I'll give you a 100% confidence interval that stretches from negative infinity to positive infinity. For instance, let me guess tomorrow's high temperature for the day. I'm going to give you a 100% confidence interval that tomorrow's high temperature will be between negative infinity and positive infinity, and I am 100% confident in that. Intervals that are so wide that you're 100% confident become uninformative. What we are trying to do, let me see if I can go back to R here now. What we're trying to do is chop off some of these less likely values in the tails that theoretically stretch off to negative and positive infinity. We're trying to lose that area in the tail to give up some confidence, like narrow us down to 0.45 to 0.49. But in giving up that 5% confidence, we are narrowing this interval down such that it becomes a meaningful quantity for us.